All right, kids, as promised, here's the updated video for topic 5.2. I just want to remind everybody that this unit is about toolkits. All right, so it's about Hess's law, enthalpy of combustion formation, and Born-Haber cycles and spontaneity. Seems like a lot, but it's not that big of a deal. So basically, we're just giving you a bunch of tools for your toolkit, and you're going to calculate delta H using all these different tools, and this video is basically about all the tools you're going to use. All right, so we did talk about Q equals MC delta T, the experimental method, as well as average bond enthalpy in topic 5.1. All right, so one thing you could use is something called a thermochemical equation. A thermochemical equation is just a balanced chemical equation that gives you the thermodynamics for said process. All right, so there's two ways you could see it. One, you could either be given the equation with a delta H value, or the delta H value could be embedded into the equation. So here it's the same reaction, the formation of sulfur trioxide from sulfur dioxide and oxygen. Notice the delta H value is negative 198 kilojoules per mole. If delta H is negative, that makes it exothermic, which means heat is a product. So you can see it as two ways. One with just the equation and the delta H, or delta H embedded in the equation. If it's endothermic, it would be a reactant. All right, so delta H is, of course, proportional to the amount of moles of reactants and products. So we get some stoichiometric conversion factors to use here. I could say that 198 kilojoules of energy is equal to 2 moles of SO2, 1 mole of oxygen, or 2 moles of SO3 being formed. All right, get your stupid ugly mug out of the way. All right, so here's an example of using that. It says how much heat in kilojoules would be released if you made 25.0 grams of sulfur trioxide, and we're given the molar mass is 80. So if I knew how many moles of sulfur trioxide were formed, then I could easily calculate the heat. Remember to go from mass to moles. Moles will be the mass divided by the molar mass of the compound. So that means we have 0.313 moles of sulfur trioxide formed. Note here in our measurement we have 3 sig figs, so I rounded my answer of moles to 3 sig figs. And then all we got to do is multiply the number of moles by delta H, in this case 0.313 times 198. Notice we eliminated the negative sign because we don't really use the concept of negative energy in our class. I don't even know if it's actually a concept. All right, so in my calculator I get 61.974. Again, 3 sig figs. So I round my answer to 3 sig figs, becomes 62.0, but box around it because that is your answer. All right, next we can calculate the enthalpy change for a reaction by looking at enthalpy of formation data. So enthalpy of formation is denoted as a delta H theta with the subscript F. The F is for formation. So enthalpy of formation is the energy that is released upon the formation of 1 mole of a compound in its standard state. So the equation we use, the tool for your toolkit, is the enthalpy change of a reaction will be equal to the sum of all the enthalpy of formations of the products minus the sum of all the enthalpy of formations of the reactants. So you can find these values for enthalpy of formation in table 13 in the data booklet. Now I'm not going to use a camera to show you where these values are in the data booklet. You're just going to have to trust that I'm looking up that I'm using the correct values. Now, one quick note, in the data booklet, those values are all for 1 mole. 1 mole. 1 mole of the compound stated. So when we're getting the sum, we have to consider the stoichiometric coefficients, which tell us the number of moles. Now, why would we do this over using average bond enthalpy? Again, to use average bond enthalpies, the substances have to be in the gas phase. And also, the values themselves are an average of a bunch of different compounds, whereas these enthalpy of formation values are specific to the compounds in question in their standard states. All right, so just a heads up, you're not going to see any elements in table 13 because elements do not have enthalpy of formation. They are formed in nuclear processes in the heart of stars or during the massive explosion of stars. So the elements were already here when we started doing the chemistry, so we don't have to consider their formation. All right, so here's an example of doing this type of calculation. It says use enthalpy of formation values to calculate the enthalpy change for the reaction for the combustion of methane. Note the states. Sometimes you'll see the water being formed as a liquid and sometimes as a gas. Here it's a liquid, so when we get the value from the data booklet, can I shrink this picture of me? Can I shrink myself? Oh, I can. There we go. we have to make sure we get the value for liquid water and not steam. So the equation we use is products minus reactants. My products are 1 mole of carbon dioxide and 2 moles of water. So when 1 mole of methane and 2 moles of oxygen. Again, oxygen as an element will not have an enthalpy of formation. So it's negative 394 plus 2 times negative 286. Those are the enthalpy of formation of carbon dioxide and liquid water, respectively, minus the enthalpy of formation of methane, which is negative 74. When you punch the values into your calculator, you get negative 892 kilojoules. All right, so the beautiful thing about this, if you're using formation data, you can actually check your answer in the data booklet. This is the enthalpy of combustion of methane because it's the energy released when we burn 1 mole of methane. If you look in the data booklet, it says that value. In table 14, it says it's negative 891. So this method works pretty good. All right, we can also use enthalpy of combustion data to calculate the enthalpy change for a reaction. So it's a really similar but a little bit different. So the definition of enthalpy of combustion is the energy that is released upon the combustion of 1 mole of a compound in its standard state. The equation we use, the tool for our toolkit, is very similar to the last tool but different. The last tool was the sum of the enthalpy of formation of products minus reactants. This is the sum of the enthalpy of combustion of reactants minus products. Where are these data going to be found? Enthalpy of combustion is in table 14. All right, so here's an example of doing this. It says determine the standard enthalpy change of formation of propane in kilojoules per mole using this information and data from table 14 in the data booklet. All right, so the first thing we always got to do if we're calculating the enthalpy of formation, we need those coefficients, so we have to write an equation for the formation. So if we're forming propane, it'll be 3 carbon atoms plus 8 hydrogen atoms to make 1 mole of C3H8, or 3 moles of C and 8 moles of H to make 1 mole of C3H8. So when we plug in, the equation we use is enthalpy of combustion of reactants minus the sum of the enthalpy of combustion of the products. So my reactants are 3 moles of carbon and 8 moles of hydrogen. So it's 3 times the enthalpy of combustion of carbon plus 8 times the enthalpy of combustion of hydrogen minus the enthalpy of combustion of propane. When you do that, you get negative 1251. Put a box around it because it's your answer. Now, just a little note here. That value, 1251, is nowhere near the actual literature value. It's about twice or 3 times as big. So I think the discrepancy really there comes from the fact that we have to be plugging in these values at their standard states. I don't know if, I know that this process, just like mixing carbon and hydrogen, does not make propane. So I imagine that the carbon maybe in the data booklet is not in the state that it would be, or blah, 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 blah. I'm sure that the equations that the IB uses and the reactions will all make sense, but I tried a few of them and none of them were working and I just gave up. All right, next tool in your toolkit is called Hess's Law. So Hess's Law says that the enthalpy change of a reaction is equal to the sum of the enthalpy changes of all the steps that go into making that compound or whatever. All right, so basically what we're going to get is a series of individual equations, the steps or the mechanism that leads up to the overall equation and the overall equation. And the goal here is to make all the reactants and products in our steps match the reactants and products in our overall. To do this, we got to manipulate equations. There's 2 ways we're going to manipulate the equations. 1, we could reverse the equations. And 2, we could multiply or divide the equations by a factor that makes them match the overall. So let's look, so basically the goal here is to make it so that the stoichiometric coefficients on all the reactants and products in the steps are the same as those in the overall equation. All right, so let's look at just a general example here without any values just to see what we would do. All right, actually this is just to see what happens when we manipulate the equation, sorry. So our equation is the same one from the beginning of this discussion. 2 moles of SO2 plus O2 making 2 moles of SO3. And the delta H value for that process is negative 198. So if we reverse the reaction, then we just reverse the equation. So now I've got 2 moles of SO3 on the reactant side and those things on the product side. Well, remember, whatever the delta H value is for one process, the opposite process is negative. So if we reverse the reaction, we just reverse the sign of delta H, so negative 198 becomes positive 198. We could also multiply or divide our equation to make it match. So if, let's say, we had our overall had 1 mole of SO2, half a mole of O2, and 2 moles of SO3, we would divide it by 2. If we divide the coefficients by 2, we also divide the delta H value by 2. So negative 198 becomes negative 99, half the value. All right, so here is the generic example just with A, B's, and C's. All right, so the first thing we got to do is look at our overall. We start with a reactant and find it in the steps. We have to consider two things when we find the reactant or product in the steps. We have to make the stoichiometric coefficient match what's in the overall, and we have to make its position in the equation the same as well. So if in your overall it's in the reactant side, and in the step it's on the product side, then we have to actually flip that equation, so we would reverse the value of A. All right, so the next reactant I see is O2. Notice how you see oxygen in two different steps. That makes this a little bit challenging to work with. So if you ever see the same element in two steps, skip it for the time being. It'll usually work itself out. All right, so the next product I see is carbon dioxide. In my overall, I have 1 mole of carbon dioxide on the product side. I find carbon dioxide in reaction B. There's 1 mole of it on the product side, so we're just going to leave the value B as it is. The final product is 2 moles of H2O. I find water in reaction C. In the overall, there's 2 moles. In the step, there's 1 mole, so I have to double the value for C. And then to solve for delta H, since Hess's law is the sum of these steps, we take the negated value for A, add it to B, and add it to double the value for C, and that will give us delta H. All right, so general tips for doing Hess's law. First, start with the first reactant you see in the equation. Find it in the given equations and manipulate that equation to make it match the overall. Do the same thing with all the reactants and products. If you find a reactant or a product that is in more than one equation, usually it'll be oxygen, but sometimes not. Skip it for the time being because it'll usually work itself out. I actually want to go back to the previous slide just to kind of show you how that works. When we left B as it is, what we were saying is that there was 1 mole of O2 in that step. In the overall, there's 2 moles of O2, and in that step, it's only a half. So we have to double that one to make it add up. Ooh, so yes, it all makes sense. All right, and finally, if you have more than 2 equations, you can add them up and simplify after the second to see where you're at. So for example, once we knew we were going to leave B alone, and we knew that we needed to have 2 total moles in our overall, well, if that's going to be 1 mole, then that would have to be 1 mole as well, so we would have to double it to get a combined amount of 2 moles. So multiple ways to do it. All right, so I want you guys to try this one on your own. Even if you were present in class, still pause the video and see if you can work it out, because Hess's law is not the hardest thing we do in this class. All right, so the first reactant I see is ethene, C2H4. The equation I see ethene is reaction C. There's the coefficient matches, there's 1 mole, but it's on the wrong side. Oh, hold on. Actually, the first thing I wanted to say is, even though these are actual values here and they're not in terms of A, B, and C, I like to label them as A, B, and C, because when I'm setting up my delta H calculation, I set up a little one in terms of A, B, and C, and then I just plug the values in. It makes your life a little bit easier. All right, so the first thing I see, I'm getting ahead of myself, is ethene in the overall. There's 1 mole of it, but it's on the wrong side, so I got to reverse that reaction, so I'm going to reverse the value for C. Fluorine I see in 2 different equations, so I'm going to skip it for now. CF4 is in reaction B. It's on the correct side of the equation on the product side, but in this step there's 1 mole, and the overall there's 2 moles, so I got a double B. The final product I see is hydrogen fluoride. In the overall, I have 4 moles on the product side. In the step, I have 2 moles on the product side, so I have to multiply A by 2. So when I set this up, it's just going to be C, which is positive 52, negated, so negative 52, plus 2 times negative 680, because we had to double B, plus 2 times negative 537, because we had to double A. When you plug the values in, you get negative 2486. I did not apply a change for sig figs here because I don't really care. All right, the final tool we're going to talk about is something called a Born-Haber cycle, or an energy cycle. So essentially, a Born-Haber cycle is a visual representation of Hess's law. So it's really the same thing. We either add or subtract values based on their thermodynamics and how much of blah, 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 blah. I'm getting ahead of myself. Now, before we can talk about Born-Haber cycles, we got to define a few more enthalpy changes since we're going to be dealing with these in the cycle. The first one is called lattice enthalpy. Lattice enthalpy is the energy that is required to convert 1 mole of an ionic compound into free gaseous ions. So equations that would represent lattice enthalpy are as follows. Solid sodium chloride getting converted into free gaseous ions. So sodium ions in the gas phase plus chloride ions in the gas phase. If it were calcium chloride, it would be 1 mole of calcium ions and 2 moles of chloride ions in the gas phase. If it's magnesium nitride, it would be 3 moles of magnesium ions plus 2 moles of nitride ions in the gas phase. Now, the thermodynamics of this step, this is always going to be an endothermic process because it takes energy to break that ionic bond and blah, blah, blah. All right, the next type of energy change, enthalpy change, is called the enthalpy of atomization or sublimation. That is the energy that is required to convert 1 mole of solid metal atoms into free gaseous atoms. So these equations are pretty simple, just sodium solid going to sodium gas, calcium solid going to calcium gas, etc. The thermodynamics, these are always endothermic as it takes energy to vaporize a solid. Moving right along, electron affinity is the energy that is released or sometimes absorbed when 1 mole of electrons are added to a neutral atom. So if we have diatomic chlorine becoming 2 chloride ions, diatomic nitrogen becoming 2 nitride ions. Now, again, usually this is exothermic because it's the opposite of ionization energy. But sometimes the second electron or second moles of electrons actually has a positive electron affinity. But again, those will be given to you if you need them. So the steps involved, we're going to basically undergo those processes to turn our solid metal and our nonmetal into gas phase ions. We then connect the gas phase ions to the compound itself to get the lattice enthalpy. I expect none of that to make any sense, but it's not a big deal. It will eventually. All right, so the first thing we got to do is work on the metal. We're going to start with the solid metal. The first thing we got to do is turn it into gaseous metal. So that'll be the enthalpy of atomization / sublimation. Those values are not in the data booklet, so they'll either have to be given to you or they'll be the values that you're trying to calculate. The next thing we got to do is turn those gaseous metal atoms into gaseous metal ions so that we're going to use the first ionization energy. Now, if it's an ion with an oxidation state greater than 1, you'll need a second and or a third ionization energy as well. Some of those are given in the data booklet. If not, they will be given to you. All right, so that is all we got to do to turn our metal into a gaseous ion. So for the nonmetal, we got to do the same thing as well. But the nonmetal is a diatomic molecule, so the first thing we need is the bond enthalpy, which is the energy change associated with separating the atoms in the diatomic molecules. You can find bond enthalpy in table 12 of the data booklet. And finally, once you have your gaseous nonmetal atoms, we have to turn them into gaseous anions. So we have to add electrons, so we'll need the electron affinity, which you can also find in table 9 in the data booklet. All right, so when we look at the cycle, this is a two-dimensional cycle, and we use arrows to show the processes. It's all done on a spectrum of energy. So if the arrow points up in your spectrum, that means it's an endothermic change. And if it's exothermic, that means the arrow points down. So the steps for the metal, the enthalpy of atomization and the ionization energy are both positive. So those arrows will always point up in the cycle. For the nonmetal, bond enthalpy is endothermic, positive enthalpy change, so it will also point up. Electron affinity, though, is negative for the first electron. The second one can be positive, but because it's negative for the first one, it'll be pointing down and blah, blah, blah. All right, so you guys do not have to create an energy cycle, but it helps to actually watch it be created so you can see how it works. The first thing I have, if we're going to do an energy cycle for the formation of lithium fluoride, is an equation that represents that formation process. Now, the lattice enthalpy is always for the breaking of 1 mole of, or for the formation, of 1 mole of the compound So here are those dreaded fractional coefficients. We'll have 1 mole of solid lithium and half a mole of diatomic fluorine to make 1 mole of lithium fluoride. This arrow represents the enthalpy of formation. That's always an exothermic process, which is why the arrow points down. All right, so once we have this, the formation equation, let's start working on the metal. The first thing we're going to do is turn those solid lithium atoms into gaseous lithium atoms. We have not done anything to the nonmetal yet, so the half mole of fluorine just comes on up, and that arrow represents the enthalpy of atomization, which is 159 kilojoules per mole of lithium atoms. The next thing we have to do is take those gaseous lithium atoms and turn them into gaseous lithium ions. Again, we didn't do anything to the fluorine, so it just comes on up there. This arrow here represents the first ionization energy for lithium, which is 520 kilojoules per mole. We now have our gaseous metal atom, so now we have to make our gaseous nonmetal, or gaseous metal ion, so now we have to make our gaseous anion. So the first thing we have to do is break the bond between those fluorine atoms. The value in table 12 of the data booklet is for 1 mole of fluorine-fluorine bonds. That's a half mole. So we actually may need half that value, and half F2 goes to 1F. So the value in the data booklet is 159. We get half that value for our energy cycle. Finally, we've got our fluorine gaseous atoms. We got to turn them into fluoride ions. So F gas becomes F1 minus gas. That arrow represents the electron affinity. And finally, now we have our solid lithium fluoride going to our gaseous ions, which represents the lattice enthalpy. The lattice enthalpy for lithium fluoride is 1049. All right, so again, you guys do not have to make these cycles, but you do have to calculate the value of arrows in these cycles. When you get the swing of it, it's actually super duper easy. Because when we're solving, all we got to do is identify the arrow for which we're being asked to solve. In this case, we're being asked to solve the enthalpy of formation of lithium fluoride. We start at the back of the arrow and travel around the cycle all the way to the front of the arrow. Every time we encounter a value that is represented by these arrows, we either add or subtract the values. If we're traveling in the same direction as the arrow, we add the values, and if we're going against the arrow, we subtract the value. So when we solve, we're going to solve for this arrow right here, the enthalpy of formation. So we start at the back and travel around. The first arrow I encounter is the enthalpy of atomization. We're going in the direction of that arrow, so we just start with 159. The next arrow I encounter is the ionization energy. We're going with that arrow. So I add the value 520. As I go around, the next arrow I encounter is the bond enthalpy. We're going with it, so we add 1/2 times 159. Going around the cycle, we're going with the activation or the electron affinity, arrow. So we add negative 328, same thing as subtracting 328. And then the last arrow we encounter is the lattice enthalpy. We're going against it, so we subtract the value, minus 1049. And you get the enthalpy of formation is negative 618.5. If you look it up on the internet, that's actually really close to what it actually is. Science works. All right, so take a moment and see if you can solve here for the enthalpy of atomization. All the cycle's already made, the values are already in. You just got to calculate the value of that arrow. Start at the back, go to the beginning, pause the video, get it done, and you'll see how easy this is. 1, 2, 3, 4, 5. I think that's enough time. All right, so when we solve, this is the arrow. First arrow I encounter, we're going this way around the cycle now, is the enthalpy of formation for calcium chloride. Since we're going with the arrow, we just include that value, which is negative 795.8. Next arrow is the lattice enthalpy. We're going with it, so we add 2271. Next arrow I encounter is the activation energy, or excuse me, I always say activation energy, the electron affinity. We're going against that one, so we have here, it's 2 times negative 349. We need 2 times positive 349. We flip the value. Next arrow I encounter, we're going against, and it's 242, so we subtract 242 minus 590 minus 1145, and you should have gotten 196.2 kilojoules per mole. If you did, fantastic. All right, final thing we got to talk about is entropy. Entropy is denoted with a capital S, and the simplest definition of entropy is the amount of disorder in a system. So if you think about sand versus a sandcastle takes those sand grains and orders them versus a pile of sand, which is more random. So a pile of sand has more entropy than a sandcastle. All right, so it's the disorder in a system, and entropy increases as you go from solid to liquid to gas. All right, so if we look at these examples of these reactions, we can determine whether or not entropy increases or decreases just by looking at what we've got. So in the first equation here, we have nitrogen and 3 moles of hydrogen making 2 moles of ammonia. Since we start with 4 moles of gas and end up with 2 moles of gas, delta S here is actually negative. Less gas has less disorder than more gas. Here we're going from liquid to gas. Entropy increases as we go solid to liquid to gas. So that means the change in entropy when you boil a liquid is positive. And for the last example, we have 1 mole of solid calcium chloride going over to 1 mole of solid calcium oxide and 1 mole of carbon dioxide. The gas has more entropy than the solid, and we're going from 1 to 2. So delta S there would be positive. All right, this video has taken a lot of energy for me to make, and it's already at 26 minutes, so we're going to go through the rest of this fast. There are 3 main things that can affect the amount of entropy or influence the entropy in a reaction. One is the number of particles. More particles is more disorder, just like more cars is more traffic. The state of the particles, because gases have the highest disorder, solids have the lowest disorder. And finally, the available energy of the particles. Remember, the temperature is connected to the motion of the particles. Faster moving particles is more random, less ordered. So increasing, temperature increases entropy. All right, so how do we actually calculate entropy? The same exact way we calculate enthalpy. If you look in the enthalpy table 13, the formation data, you also have entropy of formation there. So we would calculate it with the sum of the delta S values of products minus the sum of delta S values of the reactants. All right, so a very important note about the units. If you look in table 13, you'll see that delta S has units of joules per mole Kelvin. But delta H and this thing we're going to talk about next, delta G, both have units of kilojoules per mole. You have to make sure all the units of entropy and enthalpy are consistent. So you always have to divide that delta S value in table 14 by 1,000 before actually using it. All right, so what makes a reaction thermodynamically favorable? The natural drives of the universe. The second law of thermodynamics says that everything in nature tends towards stability and disorder. So entropy naturally increases over time. So which type of reactions lead to more stability? Exothermic reactions, ones where delta H is negative. And which type of reactions lead to more disorder? Well, any reaction where delta S is positive. So if delta H is negative and delta S is positive, then the thermodynamics of that process are favorable, so the process will be what we call spontaneous. It will just happen. All right, so let's look at a bunch of all the possible combinations of signs of delta H and delta S. So in reaction 1, we have delta H values. Oh, wait, hold on. Sorry, I'm getting ahead of myself. Teaching for a half hour straight is tough. All right, so that delta G thing we talked about earlier is called Gibbs-free energy. And Gibbs-free energy can be calculated using this equation, which is in the data booklet. Delta G theta equals delta H theta minus T delta S theta. So we can determine the spontaneity of a reaction by looking at the value for delta G. If the sign of delta G is negative, that tells us that the reaction is spontaneous, which means under the right conditions, it will just happen all on its own. All right, so now let's look at reaction 1. All right, so first thing I want to look at here and talk about is the math. So if delta H is negative and delta S is positive, let's imagine plugging those values into this equation. If delta H is a negative value and delta S is a positive value, we'd be taking a negative and subtracting a positive, so it's negative minus negative, which will give us a negative value every time. That means that if delta H is negative and delta S is positive, it will always be spontaneous because both delta H and delta S are going with the flow of the universe. They are both thermodynamically favorable for that process, so the process will just happen all on its own. If we look at the opposite here, where delta H is positive and delta S is negative, well, let's consider the math. If delta H is a positive value and delta S is a negative value, that would be minus a minus, which would make both of these factors positive, which means delta G would always be positive. Now, that means the reactions are never spontaneous because both delta H and delta S are going against the flow of the universe. Now, if we look at reaction number 3, here we have both delta H and delta S being positive. So this can actually lead to either a positive or a negative value for delta G. If delta G is going to be positive, remember we only have 2 factors here. If it's going to be positive, then the delta H factor must be, or excuse me, the T delta S factor must be greater than the delta H factor. So basically, if delta H is positive and delta S is positive, well, if we want this thing to be negative, sorry, I said positive before, if we want it to be negative, this T delta S factor would have to be larger, which means we would have to have a very high temperature. So in this particular process, delta H is not favorable because it's positive, but delta S is favorable. So as long as the temperature is very high, delta G will be negative, so the reaction will be spontaneous. So there's another way I like to think about this whole positive, positive, negative, negative thing. And that is just to think about a process that would have a positive value for both delta H and delta S. A perfect example of that is boiling a liquid. Boiling a liquid, going from liquid to gas, is an endothermic process with the positive delta H, and gas has more entropy than liquid, so it also represents an increase in entropy. Does boiling water happen spontaneously? No, it only happens spontaneously at higher temperatures. All right, so if we look at the combination of negative values for delta H and delta S, again, it could be either or. But if delta G is going to be positive, this factor needs to be greater than that factor. If delta G is going to be negative, this factor would have to be greater. All right, so delta H is favorable here and delta S is not favorable. So these processes will only be spontaneous at lower temperatures. Again, think about a process where both delta H and delta S are negative. Would be the opposite of boiling, freezing a liquid. In order to freeze a liquid, you got to take energy out of the liquid, so that is an exothermic process, and solids have lower entropy, so going from liquid to solid would represent a decrease in entropy. Does a liquid freeze spontaneously? Sometimes, but only at lower temperature. So the way I like to remember these is you just got to know what the universe prefers, which delta H and delta S values are favorable, and then you can figure out the rest, because positive and positive means high temperature to me, and negative means low temperature. All right, finally, oops, hold on. My transitions are a little bit messed up there. All right, so if we just look at examples, for this reaction, mixing hydrated barium hydroxide with ammonium nitrate, that is an endothermic reaction. If you mix those two solids together, it does become cold, but it only happens at higher temperature. Probably because both of these are ionic, and you got to break the lattice. Who even knows? But anyways, if we look at water going from solid to liquid, that's melting, which is endothermic, and represents an increase in entropy. Liquids only melt at higher temperatures, or solids only melt at higher temperatures. Video is too long. All right, this is the opposite. This is freezing water, both negative, which only happens at lower temperatures. And this process here, putting calcium chloride in water, is an exothermic dissolution. Right? And it's an increase in entropy because we're going from 1 mole of reactant to 3 moles of product, and aqueous is more disordered than solid. So that process is always spontaneous. And finally, if it's spontaneous, it just means that under the right conditions, it will happen all on its own. It doesn't mean it's going to happen fast. We'll talk about that in Unit 6. Hopefully this video helps. 34 minutes. Hopefully you watched it all. And sorry about the fewer ad breaks for longer videos. We all know that's BS. Anyways, thanks for watching, and I'll see you guys in class.